Let's look at again our simple acid-base reaction. HA plus water goes to A minus plus H3O plus. So here's our acid, here's our base, here again is our conjugate base, and here is our conjugate acid. So we can, as chemists, we can quantify this equilibrium. Now we're not going to do this a bunch in organic chemistry, but we need to be familiar with the steps. So for any equilibrium constant, how do we calculate that? Well, it is simply determined by the concentrations of the products times the concentration of H3O plus divided by the concentrations of the starting materials. So the concentration of HA times the concentration of water. That's our K value. Now, as it turns out, typically in chemistry, the concentration of water is pretty high relative to your acid. And in that situation, this reaction will only consume a very small amount of your water, so the concentration of water is roughly constant. And so we get the water out of this equation, we multiply both sides by water, and we get something, and I've left a little space over here because I'm going to put something over there. K times the concentration of water equals concentration of our conjugate base times the concentration of hydronium, which is our conjugate acid, divided by the concentration of our original acid HA. And this entire thing is roughly constant because the concentration of water is roughly constant. And so this is now what we call Ka. So when people talk about acid-base equilibria, they don't typically discuss K, they talk about Ka, which is simply K with it's been multiplied by the concentration of water. Now, as it turns out, Ka values can really range. So if we look at this equilibrium, let's say our equilibrium constant is 10 to the minus 7th. Well, 10 to the minus 7th is a really small number. That means this reaction, the reaction barely progresses at all. So this is the equilibrium lies to the left. And you could also have a value for K that could be 10 to the 10th. So 10 to the 10th is a very large number, so our K value is huge. And this would be a case where the equilibrium lies really far to the right. Because our equilibrium constants, K and therefore Ka, are both going to be really wide-ranging numbers, people often will take the logarithm of this to define a new term, which is probably more familiar to you, which is pKa, the negative log of Ka. So the pKa of, if the equilibrium, if the Ka is minus 7, 10 to the minus 7th, well, log of 10 to the minus 7th is simply minus 7 itself. A logarithm is an exponent. Minus 7 times minus equals plus 7. So this would be if the equilibrium lies to the left, then this would be a weak acid. And so here's the pKa of a typical weak acid. If we go through the same steps and have a Ka of minus 10, the pKa of 10 to the plus 10th is going to be negative 10. So if pKa is something like negative 10, the equilibrium lies to the right, and this would be a very strong acid. And so negative 10 would be representative of a much stronger acid. So this is how we discuss equilibrium, acid-base equilibria quantitatively.